There is a molecule so ordinary, so utterly familiar, that we barely give it a second thought. It falls from the sky, it flows from our taps, it makes up the majority of our own bodies. We swim in it, cook with it, give it to our children without a moment of hesitation. And yet, when you sit down and examine this molecule with the rigorous, unblinking eye of physics and chemistry, something extraordinary happens. The molecule stops looking ordinary. It starts looking like one of the most chemically aggressive, structurally bizarre, and physically paradoxical substances that the laws of the universe permit to exist. The molecule is water, 2 hydrogen atoms bonded to a single oxygen atom, 3 atoms, 1 molecule, and an almost implausible catalog of properties that, when you examine them one by one, begin to feel less like the background scenery of life and more like an arsenal of physical forces that the cosmos assembled with breathtaking precision. To understand why water is so unusual, we have to start with something that most people never think about when they turn on a faucet. We have to think about the shape of the molecule itself and about a force called electronegativity. Oxygen is one of the most electronegative elements in the periodic table. What that means in the language of atomic physics is that the oxygen atom in a water molecule pulls the shared electrons in its 2 bonds dramatically toward itself, away from the hydrogen atoms. The result is that the oxygen end of the molecule carries a slight negative charge, while each hydrogen atom carries a slight positive charge. The molecule is electrically lopsided. And because the 2 hydrogen atoms are arranged at a specific bond angle of roughly 104 degrees, the molecule is not just lopsided but bent, like a tiny angular wing with a negative pole at the top and 2 positive poles spreading outward below. This shape is everything. This shape is the origin of virtually every remarkable property that water possesses. Because when you assemble an enormous number of these bent, electrically lopsided molecules together, something remarkable begins to happen. The positive hydrogen end of one molecule is attracted to the negative oxygen end of a neighboring molecule, and a bond forms. Not a full covalent bond of the kind that holds atoms together inside a molecule, but something intermediate, something weirdly persistent. This is the hydrogen bond, and it is, by any physical measure, an extraordinarily strong intermolecular force for molecules as small as water. It is what makes water molecules cling to each other with unusual tenacity, what makes them reluctant to separate, what makes the liquid cohesive in a way that is, when you compare it against other molecules of similar size, frankly, anomalous. Consider what these hydrogen bonds mean in practice. Every time you heat water, you are not just making the molecules move faster. You are fighting against an entire network of hydrogen bonds, a constantly shifting, constantly reforming lattice of attractions that resist being broken. This is why water has such a remarkably high specific heat capacity compared to other liquids. It takes an enormous input of energy to raise the temperature of water by even a modest amount, because so much of that energy goes not into speeding the molecules up, but into disrupting these hydrogen bonds. The ocean stores heat in a way that no other substance on this planet could, given its abundance. The temperature fluctuations on Earth are buffered, moderated, made compatible with biological stability, because water is physically reluctant to change its temperature. Remove the oceans, and you remove this thermal buffer. The surface of the planet would swing between extremes of heat and cold, so violent that the chemistry of life would almost certainly fail. But there is something even more surprising embedded in the physics of hydrogen bonding, something that overturns one of the most intuitive assumptions you might have about how matter behaves. When most liquids freeze, when the molecules slow down enough to lock into a solid arrangement, they pack together more tightly. The solid is denser than the liquid. This is what you expect. This is what happens with most substances. But water does the opposite. When water freezes, the hydrogen bonds force the molecules into a rigid, open, hexagonal lattice. The ice crystal is actually less dense than liquid water. It floats. This is not a minor quirk. This is a physical property with consequences that cascade through the entire history of life on this planet. When a lake cools in winter, the ice forms at the surface and stays there, insulating the water below. The liquid water beneath the ice layer remains liquid, remains warm enough, remains a viable environment for biology to persist through the cold season. If ice sank, as common physical intuition might suggest it should, lakes would freeze from the bottom up. The entire body of water would eventually solidify. The biology within it would be annihilated every winter with no insulating layer to protect it. The fact that ice floats is not a lucky accident. It is a direct physical consequence of hydrogen bond geometry, and it has shaped the conditions under which life has been able to exist on this planet in ways that are genuinely difficult to overstate. Now we come to the aspect of water that most closely approaches what a physicist might call dangerous. Not dangerous in the simple sense of drowning, though we will get to the macroscopic physics of that shortly. Dangerous in the chemical sense. Dangerous in the sense that water is, at the molecular level, one of the most capable dissolving agents that chemistry permits. The same electronegativity that makes water molecules stick to each other with unusual force also makes them extraordinarily effective at pulling apart other molecules, at inserting themselves between ions, at surrounding charged particles, and neutralizing the forces holding them together. Sodium chloride, table salt, is held together by powerful ionic bonds. The positive sodium ions and the negative chloride ions attract each other with forces governed by Coulomb's law. And yet, when you place salt crystals in water, those bonds dissolve almost immediately because the water molecules orient themselves around each ion. Their negative oxygen poles facing the positive sodium ions. Their positive hydrogen poles facing the negative chloride ions, shielding each ion from the attractive pull of the other. The crystal disassembles ion by ion until it has completely dispersed into the liquid. This capacity to dissolve is not limited to simple salts. Water dissolves an extraordinary range of substances, minerals, gases, acids, bases, biological molecules of considerable complexity. It is this very capacity that makes water the medium of cellular chemistry. Every reaction inside a living cell happens in an aqueous environment, in water. Nutrients dissolve in water to reach cells. Waste products dissolve in water to be carried away. Signaling molecules dissolve in water to communicate between cells. The entire molecular machinery of biology runs on water as its solvent. And it runs on water specifically because no other molecule that is liquid at the temperatures compatible with Earth's surface chemistry is anywhere near as effective at dissolving the range of substances that life requires. But this same dissolving power is also genuinely destructive. Water attacks rock. Water, not quickly by human timescales, but with a physical inevitability that geological time makes visible. The process is called chemical weathering, and it works through water's ability to dissolve minerals, to insert hydrogen ions into crystal lattices, to hydrolyze the silicate bonds that hold rock together. Mountain ranges are worn down. River canyons are carved. Landscapes are transformed by what is essentially the slow chemical aggression of water against solid matter. The Grand Canyon is not the story of mechanical erosion alone. It is the story of water chemistry, of a liquid that is fundamentally reactive, acting on stone over millions of years. Even concrete, one of the most durable materials human civilization has produced, is slowly hydrated, slowly attacked, slowly weakened by the water that permeates it. Water does not corrode in the way that acids do, with dramatic, visible violence. It corrodes with patient, persistent molecular persistence, and the scale of what it ultimately destroys is correspondingly vast. There is something even more fundamental to consider, something that operates at the boundary between physics and biochemistry. Water is not merely a passive solvent for biological reactions. It actively participates in them. There is a class of chemical reactions called hydrolysis, and the name tells you everything. Hydrolysis means splitting with water. In your digestive system right now, the long chain molecules of the proteins and carbohydrates and fats you have consumed are being cleaved apart, broken into their component units by reactions in which a water molecule attacks a chemical bond and inserts itself into the break. The bond snaps. The protein chain fragments into amino acids. The starch dissolves into sugars. The fat breaks into fatty acids and glycerol. Water is not watching this happen from the sidelines. Water is the chemical agent doing the cutting. It is the molecule wielding the molecular scalpel. And outside of biological contexts, this same hydrolytic chemistry degrades materials, breaks down polymers, destroys structures that were built to last. The physical world slowly yields to water's chemical insistence. And then there is the sheer physical force of water in bulk, the macroscopic expression of all that molecular cohesion aggregated to human and geological scales. Water moves with a density close to 1,000 kilograms per cubic meter. It is, by the standards of the forces a human body can withstand, extraordinarily heavy. A cubic meter of water, a box roughly the size of a washing machine, weighs a metric ton. A wave breaking on a coastline carries kinetic energy proportional to the mass of that water multiplied by the square of its velocity. The forces involved are not subtle. A rogue ocean wave, a tsunami, a flash flood, all of these are fundamentally expressions of the same molecular cohesion, the same hydrogen bond network that makes water reluctant to be torn apart, now operating at scales where that cohesion translates into mechanical force that can move boulders, collapse buildings, reshape coastlines. The physics of drowning specifically illuminates water's danger with particular clarity. The human respiratory system is built around the exchange of gases across a thin membrane. Oxygen from the air crosses into the blood, carbon dioxide crosses out. This process requires that the membrane remain a gas interface. Water, because of its extraordinary surface tension, another consequence of hydrogen bonding, does not easily allow gases to pass through a thin liquid layer. When water fills the lungs, it does not simply crowd out the air. It creates a chemical barrier that gas exchange cannot penetrate. The surfactant molecules that normally keep the lungs' air sacs from collapsing are overwhelmed. The air sacs collapse. Oxygen cannot reach the blood. And the exquisite molecular precision of the entire process fails because water's physical chemistry is simply incompatible with the mechanism by which terrestrial animal respiration operates. Surface tension deserves a moment of its own attention because it is one of water's most visually striking physical properties and one of the clearest direct demonstrations of hydrogen bonding's consequences. A water molecule at the surface of a liquid body has neighbors only to its sides and below it. The hydrogen bonds that would normally pull it inward from all directions are asymmetrical. The net effect is that the surface of water behaves like a taut elastic membrane, pulling itself together with a force that is, for a liquid of such simple composition, surprisingly substantial. Insects walk on it, needles float on it. Needles. Raindrops maintain their spherical shape because of it. And when you break that surface tension, when a swimmer dives poorly and hits the water at the wrong angle with enough speed, the liquid surface does not immediately yield. For a fraction of a second, it resists, and the forces involved in that resistance are sufficient to cause physical injury. The water does not absorb the impact gently. It pushes back. All of this flows from three atoms, from a geometry of bonds established in the early universe, when the physics of electron orbitals and nuclear charge combine to produce oxygen's particular relationship with hydrogen. The properties of water are not arbitrary. They follow, with logical necessity, from quantum mechanical principles governing how electrons are distributed in atomic bonds, from the rules that govern molecular geometry, from the statistical mechanics that describe how large numbers of hydrogen-bonded molecules behave collectively. When you see a river carving through rock, when you see ice floating in a glass, when you see a wave breaking on a shore, you are watching quantum mechanics made visible at human scales. You are watching the large-scale consequences of bond angles measured in fractions of a nanometer, of electron distributions calculated in units of charge, so small they have no analog in everyday life. What makes water seem dangerous, what gives it this quality of physical power and chemical aggression, is precisely what makes it indispensable to the kind of chemistry that produces and sustains complex molecular structures. High surface tension means biological membranes can maintain their integrity. High specific heat means temperature stays stable enough for enzyme chemistry to function. The dissolving power that erodes rock is the same dissolving power that carries nutrients to cells. The hydrolytic chemistry that degrades materials is the same chemistry that breaks food into its component molecules. The danger and the indispensability are not separate features that happen to coexist. They are the same feature viewed from different perspectives. They are the same set of physical and chemical properties expressing themselves in different contexts. This is what physics teaches us when we look closely at anything we have taken for granted. The familiar dissolves, and what we find underneath is not simplicity, but a structure of extraordinary complexity, a web of forces and interactions operating at scales we cannot see, producing consequences that cascade through the world we inhabit. 3 atoms, an angle of 104 degrees, a network of hydrogen bonds. And from these elements, a molecule that has shaped the surface of every continent, filled every ocean, made the chemistry of life possible, and remained, throughout all of that, something most people regard as no more remarkable than what falls from the sky on a cloudy afternoon.